Hello everyone, today we will continue discussing the finite volume methods, and in this lecture I'm gonna talk about approximating volume integrals. So in the previous lecture we talked about approximating the surface integrals in this finite volume scheme, how we can approximate these kind of integrals which are evaluated at the surface. And now I want to talk about the volume integrals, okay? And the goal we have is estimating S phi, which is a volume integral. So it's integral over the volume V of S phi d volume. Okay. And also the phi bar is 1 over V, the volume, integral over the volume of rho phi dV. Okay, it's kind of an average. So let's see what we are gonna do for this. Let me draw one simple two-dimensional volume, but this can be of course three-dimensional, but for now I'm just doing a simple one-dimensional one. So we have a point in the middle, and then we have fluxes that go around this. So these are the fluxes. So the simplest approximation that we can have for this volume is as follows. So simplest for this volume integral, we can say SP is the integral of volume over the volume S phi dV, which is gonna be kind of SP bar times V, right? This is like an average over here. If you take the average over here and then multiply that by the volume of that is like evaluating this integral. And then we can approximate this with what? With the value of S at point P, or here, just the center, times volume. So approximating the average value of the any scalar here, or any quantity that we want to approximate. Okay, approximating that with the value here, with the value at the center. So this is center. So this approximation is exact if SP is constant. So if SP is constant within this volume, then this approximation is exact. For example, if SP here and here and here in all locations is the same, this approximation is going to be exact. Otherwise, is SP, it is a kind of arbitrary parameter, right? It can be anything like speed, or it can be temperature, it can be any variable that you may imagine. For example, humidity or whatever. So this, if it varies along this volume, for example, it is higher here than here, then this is gonna be second order. So otherwise, this is a second order scheme. Okay. So if you want to use, this is a second order scheme, a simple one. Higher order schemes require more nodes than just the center. So here we only had the center point, but if you want to have a higher order than second, then we need more points. Okay, so I'm gonna give you an example here. So let me give you here, for example, for Cartesian, if you have a Cartesian coordinate, then I can, for example, fit a function sxy. I can fit a polynomial to this xxy as follows, as this. I can say it is a0 plus a3 x squared, and I had other terms that I don't want to write, but you can write all the terms. a4 y squared plus a8 x squared y squared. So this you can find from fitting. So this is the kind of a polynomial that we can find from fitting, and then it has other terms that I haven't written, like x, xy, and other things. But for this problem, these are enough. And then for a uniform, then we can approximate SP using these points as follows. SP can be, which is the integral volume of S phi dV, is delta x, delta y. So if you don't remember what is delta x and delta y, so this is just, let me show it with another color. So this is delta x, and this is delta y. So delta x, delta y times a0 plus a3 over 12 delta x squared plus a4 over 12 delta y squared plus a8 over 144 delta x squared delta y squared. Okay, so this is the approximation we have for this volume integral, accounting for using this fitted polynomial here. So I want to write a simpler form of that. So for a uniform Cartesian grid, for a uniform Cartesian, this becomes a fourth order method. So this is going to be fourth order. And then this is going to be the integral. So we have S pi is the integral volume of S phi dV is going to be delta x, delta y over 36, 16 SP plus 4 SS plus 4 SN plus 4 SW. These are different points. I'm going to come back to them for SE plus SE plus SW plus S northeast plus S northwest. Let's see what are these. Okay, so SP, as you see, it is just a center point, right? So let me write this down. This is just center. And SS, what is SS? If you look at here, SS is just south. It is this point, okay? West, or W is west point, E is east, N is north, and then these are the corner one, northeast, southeast, northwest, and southwest, or SW, okay? So SP is the center one. These are all sides from the sides, and this is gonna be, these are gonna be from corners, okay? So this is how we represent and show this. This is going to be a fourth order. So this one was very simple, second order. But in order to become higher order, we need to use more nodes. So here I have used 1, 2, 3, 4, 5, 6, 7, 8, 9 nodes. Okay, with 9 nodes, I could get fourth order accuracy for this volume integral. And this shows that it is kind of difficult to increase the accuracy in these volume integrals.